Hey everybody, welcome back to another lecture video. This one, chapter 11, we are looking at gases. So we'll start our discussion with straws. We'll talk about how straws work, and not just any straw, but an extra long straw. So how long do you think is too long when making long straws for drinking, soda or chocolate milk or whatever? So we need to know how a straw works before we can figure out how long is too long. So when you drink from a straw, you actually remove some of the molecules from inside the straw. So you've got this cup here with liquid in it. You've got your straw. And there is air pressure that you've heard of. Air pressure is basically the weight of all of the air on top of us. So there's air right on top of Earth, and it's pushing down on us because gravity acts on air like it does on everything else. Every square inch of your body has 14.7 pounds of air weighing it down. Now, this is not just on the outside of your body, or you would get crumpled in, right? Of course, you don't notice it at all because you were born in it, you grew up in it. But you're also balanced. There's a pressure balance inside your body. You have dissolved air and gases and certain pressure to all your cells, as well as air inside, your lungs and whatnot. So there's a balance between the outside and the inside air that keeps you from being crushed. Well, there's also a balance on the outside and the inside of the straw. On the surface of the water or the soda or whatever it is, air is pushing down. But also within this, let's see, can I zoom in? Within the straw, there's also air pushing down. And so water's not going to go anywhere. Water's going to follow the pressure differences. And so what you do when you drink from the straw is that you remove that air. I thought I could erase. So maybe not. You remove that air. Okay, so it does work. Sorry. And the straw. And so by removing that air, what happens is you allow the pressure difference now to be, on the water anyways, to force the water up the straw. So you're not actually sucking the water out of the straw or the soda out of the straw or whatever it is. You're not doing that with the work you're doing. You're just removing the air. The rest of the work is done by the atmosphere. The atmosphere pushes the water. The water is no longer being balanced with its pushing, aka the inside of the straw. And so since there's nothing opposing it within that straw, water goes that direction. So that's how a straw works. Okay. Primarily nitrogen and oxygen, by the way, in the air are what's doing that. There are other gases in the air, but these are the ones. So if we had a perfectly long or a perfect straw material, and there was perfect seals between the straws, like if we were sticking straws together to make a really long straw, as opposed to, I guess, just making a really long straw that's, not segmented. How long could it be? And even if the extended straw had perfect seals and rigid walls, and there was a perfect vacuum, meaning we could have this straw, essentially, this is Earth. This is Earth. This is the straw somewhere. There's a cup or whatever down there in the Earth. There's no air up here. So that means any air within the straw has basically been sucked out of the straw. So there's absolutely no air in that straw. Nothing resisting all of the actual air that we do have from pushing whatever liquid up this straw. So how long do you think it could be? Well, in the absence of all air, a straw will only work, and this is not to scale, so I don't know why I did that, about 10.3 meters, essentially 34 feet. So why? why would anything longer than 10.3 meters or 34 feet not work? So let's talk about what pressure is. Now, I talked a little bit about the air pressure being the weight of the air, but let's get a more detailed view of what that is. So pressure is the force exerted per unit area by gas molecules as they collide with the surfaces around them. We would designate that as, newtons per meters squared, or pounds per square inch. So it's a force over some area. Now, a molecule exerts a force when it collides with the surface. The result of these many collisions is what pressure is. So on Earth at, let's say, sea level, the gas molecules in our atmosphere exert an average pressure of what we call 1 atmosphere, 1 ATM. Now, this is equivalent to a few other units, in fact, 14.7 pounds per square inch, or 760, what we call torr. These are all equivalent units. But the pressure is exerted from all of the little collisions that are taking place in these gas molecules. Now, when a straw is put into, let's say, a glass of water, the pressure inside and outside are the same, so the liquid levels on the inside and the outside are also the same. I think I have a picture of that. So when you suck on the straw, the pressure inside the straw is lowered, meaning there's no air inside running around, bouncing around, creating those forces, which is why the forces on the outside of the liquid, in this case I guess it's orange soda, actually collide with the surface enough to drive it downward and upward. So the difference in pressure is going to be what does all the work. Now, with the extra long straw, even if we had a perfect vacuum with a pump, right, sucking out all of the air, the atmospheric pressure can only push water, or in this case orange soda, up to a total height of about 10, and that's because the column of water, or soda, at 10.3 meters actually exerts the same pressure as the gas molecules in our atmosphere, meaning that the pressure caused by the weight of these guys, the downward force, is equal to any kind of upward force they would have gotten from the air pressure or the weight of the atmosphere. So when those two things balance out, then the liquid stops moving. So we're limited in how big a straw we can have by basically our gravity. If we had gravity that was much stronger, this air pressure would be greater. Of course, that would also make the column of water greater. If we had the same amount of gravity, but we had, let's say, a lot more air pressure. So if this was Earth, and this is our, this is an exaggeration of how much bubble of air we had, but if that's how much air we had, and we made it this much air, all that extra weight of the air would allow us to have even longer straws. Okay, so hopefully this has given you kind of an idea of how straws work, right? They work because of a difference in pressure. External pressure pushes the liquid up the straw. Okay, let's talk about kinetic molecular theory. Now, a model for understanding the behavior of gases is something called kinetic molecular theory. This model predicts the correct behavior for most gases under many conditions. And like other models, the kinetic model theory is not perfect, and it does break down under certain conditions. We're going to focus on our attention where it works well, obviously. The collection of particles is in constant motion. Now this just has to do with the temperature, right? We say that the temperature is a measure of the motion of particles. So for us to be even talking about gases, we're going to assume that it's anything above absolute zero and that there is motion. And so we're just going to say the collection of particles, or in this case the gases, are in constant motion. We're going to say that there's no attraction or repulsion between particles. Now, of course, this is not always true. This is mostly true because gases spend a great deal of time separated away from other gas molecules, but if they got close enough to each other, they sometimes do attract and repel. So let's just say in the ideal situation, these guys would not interact with each other. Now, another interaction is when they collide and they bounce off of each other. We're going to say these collisions are perfect and that they don't end up kind of sticking to each other a little bit or hanging on, that they, like billiard balls, will just bounce off of each other. We're going to say that there's a lot of space between the particles, more space between them than there is space, than the size of them themselves. What we mean is, if we had two particles like this, right, the space between them is actually a smaller space than the size of them. So they're really close to each other. These two particles are very, very tiny, and the size, between them is many times greater than their actual size. This is important because, again, this is going to limit the amount of interactions between them. And also when we start to talk about them, their volumes, because this is gas theory, so we're going to be using things like pressure and temperature and volume and even the number of gas particles to predict other properties, like how much space they'll take up. And so when we talk about the volume of a gas, it's important that when we talk about the gas being, let's say, in a balloon that's 1 liter, that we still know that the gas particles themselves are spread out. Because if these were all packed in on top of each other, like all clumped together, then that would be a different picture. That's not what we're talking about. This would be the volume of all the gas particles together, the gas particles only. Whereas this one, our theory is going to talk about, is going to give us gas volumes that also include lots of empty space, if that makes any sense. And the speed of the particles increases with increasing temperature. As we have more energy in the system, that's going to manifest itself as these guys having more speed. Now, I'll give you a quick equation. We use this in physics a lot to get the kinetic energy of something. But it's a good equation because it includes a mass and a velocity term. So it's 1/2 mv squared, where if you know the mass of the particle, and in our case, heavier gases like CO2 are just going to have, right, bigger m's than lighter gases like H2, hydrogen gas, which is going to have a much lower m. But if they're all in the same mixture, then they all have the same kinetic energy. So that's why I'm mentioning it. So different gases make up, air. Different types of gases. They all have different weights, but if they're at the same temperature, if they're all in the same container, they're all the same energy. That's going to translate to different velocities, though, right? For them all to have the same KE, but to have different m's, that means they're going to have different v's. As your m goes down, your v is going to have to go up. So that just means lighter particles are faster and heavier particles are slower. That being said, as I start to increase the kinetic energy of the system, that's going to increase the speed for everybody. So speed of the particles increases with increasing temperature. Of course, we know it's probably the other way around. As energy increases, the particles start moving more, and that, of course, raises the apparent temperature, or the measurement of temperature. Okay, so, So kinetic molecular theory is consistent with the property of gases. We know the gases are compressible, that gases will assume the shape and volume of their containers, that gases have low densities when being compared to liquids and solids. So just as a kind of a refresher on that, you can see gases here being compressed. Liquids, of course, they're already packed together, so they can't be compressed any further. If we were to open a gas into a jar, or have this jar and open it in a bigger room, here's that little jar. All of those gas particles would spread out. That's what gases do. They spread out. That means they take the shape of their containers. They also fill the volumes of their containers. Now, the density of the gas is not as great, meaning that or the concentration of the gas is not that great. If we were to open a gas into a big room, it would still fill up that room, but it would not have as great of a what we would call concentration. But that's not what we're talking about here. We're talking about the fact that the gas spreads out, and it does, fills up its container. As far as density goes, this means how much space the molecules themselves take up. Gases have very low density when compared with solids and liquids because of all that empty space. Remember, density is calculated by your mass over your volume, and so having a lot of empty space means a lot of accounted for volume that really doesn't have any weight to it. So making the denominator of this equation much bigger has the effect of making your density much lower. So gases have lower densities. If, for example, the liquid in a 350 milliliter can of soda, presumably the same orange soda that we were looking at earlier, were to be converted to steam, or if this was water into gaseous water, the steam would occupy a volume of 595 liters. So this is 0.35 liters, and it would take up 595 liters. That's the equivalent of going from 1 can to 1,700 cans. That's how much space they would have to take up, all of these particles, if they were to simply turn into a gas. So they would be gas form here and liquid in this one. So the density of steam at 1 atmosphere of pressure and 100 degrees Celsius is about 0.0006 grams per centimeter, which is really low. So gases tend to rise in air. Well, air itself is a gas, but what I mean is, well, I guess we would have to compare different densities of gases, but typically hot gases are going to have much lower density. So I guess that's what I was going for, is that hot gases tend to rise a lot faster. And that's because heat will expand them and increase that volume term. Pressure is the result of constant molecular motion and collisions, and that's between the atoms or molecules in the gas and between the surfaces around them. It's because of pressure that we can drink. It's also because of pressure that we can inflate, basketballs and move air in and out of our lungs. Breathing is pretty nice, right? Variations in pressure in the Earth's atmosphere actually is what creates wind, and changes in pressure help predict weather, or at least give us a little bit of an advance notice that weather's coming, or that rain, different types of weather are coming. It's all around us, even inside us, as we climb a mountain, or if you've ever gone in an airplane. There's fewer molecules per unit volume of air as the pressure drops, as we go higher and higher in the atmosphere. So climbing a mountain, or going in an airplane, there's just less gas molecules around, so the pressure's lower. And you may feel the effect of that drop in pressure as a little bit of a pain in your ears. Some people experience pain. The external pressure drops while the pressure of the air in your ear cavities is actually the same, and this creates an imbalance. The lower external pressures actually causes your eardrum to bulge outward. That can be painful. So with time, the excess air within your ear cavity escapes. Sometimes you can chew gum or yawn or something to make this happen, and this equalizes the internal and external pressures and actually relieves that pain, so the air can get out of your ear, or vice versa. If you've been at high altitude and you go to low altitude, it's the opposite. Or if you ever buy a bag of chips down here in the valley, and then you take them up to the mountains, right? That's a mountain. Here's the valley. Let's say this is high pressure. Sorry, this is low pressure up high in the mountain and high pressure down low in the valley. Well, you buy a bag of chips that was probably packaged, down here in the valley, so the inside and the outside air is balanced. Then you take it up the mountain, and your bag of chips swells up because the inside air didn't change, but now the force it's exerting on the inside of the bag is not balanced by the outside force from the low pressure. And so your stuff that's sealed can do this. And if you have a sealed container that you take up to the mountains, and it's of like shampoo, or if it's of something that's gooey and leaky, your container can actually pop open if there's air in there. And this can cause, even a trip over a mountain. So let's say you're not even going to the mountain, the mountain, you're going to the beach. But you had to drive over the mountain, your stuff can explode in your suitcase. Okay, anyways, moving on. So pressure exerted by a gas is actually defined as the force per unit area. We know that from a few minutes ago. Now, the pressure exerted by a gas depends on several factors, including the number of gas particles in a given volume. And so that seems pretty obvious. So since pressure is a result of the collisions between the gas particles and the surfaces around them, then it makes sense that the amount of particles as it goes up, that the pressure increases. So we can say that the upper container here is at lower pressure than the lower container because the lower container has more particles. And more particles will translate to more collisions per area. So if this little square right here, if we looked at it for 1 second just to have something frame of reference, it looks like there's only one collision in there. But if we do this one, it looks like the same. So bad square. Maybe I need a bigger square. So this big square has 3. This big square has 4 and some change. So more gas means more collisions, means more force in that area, so bigger pressure. The simplest, actually, sorry, I was going to give you another formula. The simplest unit of pressure is the atmosphere, ATM. This is just the average pressure at sea level. The SI unit of pressure is the Pascal, PA, the symbol. And it's defined as actually 1 Newton per square meter. I showed you this one earlier. The Pascal is a much smaller unit of pressure. 1 atmosphere is equal to 101,325 Pascal. So it's a lot easier just to say 1 atmosphere. Now, there's another pretty common unit. I mentioned torr. Let's show you where that one comes from. So the millimeter of mercury, mmHg, which is equivalent with torr, it originates from how pressure used to be measured with a barometer. Now, the average atmospheric pressure at sea level will actually push a column of mercury to a height of 760 millimeters, or about 29.92 inches. So 29.92 inches is actually how, if you look up on the Weather Channel what the atmospheric pressure is, that's usually how it's read in inches of mercury. And if we were to do this with water, if we had a water barometer, pond of water, a big tube, you have to take the air out. So, no air. And the mercury in here will actually rise, what did we say it was? About 30 feet, 10 meters or so. So imagine having a barometer that required you having to build something that was 30 feet tall. So having this thing, it's only about, 30 or, a yardstick or meter stick or so. Density of mercury is about 13.5 times that of water. And so it's actually only pushed up 1/13.5th. I don't know how to say that. 1/13 and a half, as high as water would get pushed up. So this is pretty useful. So we get these equivalencies then. We get that 1 atmosphere is 760 millimeters of mercury, and so on. So you can actually make all of these equal to each other. 1 atmosphere is 760 millimeters of mercury. 1 atmosphere is 760 torr. 1 atmosphere, 14.7 psi. If we were doing a conversion, if we were converting. In fact, we can do a conversion. Let's convert. All right. Let's do, why did I open that? Whiteboard. Let's do 0.311 ATM. That looked like paired electrons there. 0.311 atmospheres, 2 millimeters of mercury. So we're going to go 2 mmHg. Now our conversion factor is that 1 atmosphere equals 760 millimeters of mercury. So we can go and set up our conversion factor so that our units can cancel. We're left in millimeters of mercury, and if you do the math, you should get 236 millimeters of mercury. And you should be able to go from any unit to any other unit. We typically use ATM, torr, which is millimeters of mercury, mmHg. So you'll see those the most common. Okay, let's get into some of the gas laws. So let's talk about Boyle's law. Now, the pressure of a gas depends on, in part, on its volume. And so we saw already that the pressure depended on the number of particles on we're going to call that moles of the gas, and we'll call that N. But for now, we just talked about that. So let's talk about how the pressure depends on volume, in part. So if the temperature and the amount of gas stay the same, so if the temperature and moles are constant, so let's say when these are constant, meaning that when those don't change, then if you increase the pressure of a gas, it'll decrease its volume. And if you decrease the pressure of a gas, it'll increase its volume. And we can think about this in a few different ways. So one, let's look at this piston and cylinder. This is a bike pump. So on the upstroke, the increasing volume, right, causes a decrease in the internal pressure within the pump cylinder. So this draws air into the pump cylinder through a one-way valve. So again, we're saying temperature and volume are related here. I'm saying, actually, I meant to say they're proportional. So increasing the volume inside this container. So here's the top, here's the bottom. Okay. Increasing the volume creates a lower pressure on the inside. So increasing the volume had the effect of lowering the pressure inside, right? Because now for that number of gas particles, the walls were farther away. They had to move around farther to run into each other. The force over the area was less. And so then we know what happens because of a straw. This causes the air to rush inward. So that's how this bike pump works and fills up with air. Now on the downstroke, the decreasing volume. So now volume's going down. It was up here. The volume now, the lid is down here. So the whole thing got much smaller. This causes an increase in the internal pressure, right? All of that air was still inside here, so now they're bouncing around, they're colliding way more often, the force is way higher, and that's going to cause the air to flow in the opposite direction through a different one-way valve into whatever you're inflating. So the relationship between the gas properties are described by gas laws. This law is called Boyle's law. It was discovered by Robert Boyle, and it relates volume and pressure. Boyle's law, again, assumes constant temperature and constant gas particle number, or moles. And Boyle's law basically says that the volume of a gas and its pressure are inversely proportional. So that's what this little symbol here means. This means proportional to, and inversely means that if one goes up, the other goes down. So volume is inversely proportional here to pressure. I can show you another example or a couple. Adding mercury to a J tube here. So the opening is at the top, and you can see here, if I've got a J tube that has some gas and some mercury, so the mercury, gravity's pulling it down, it kind of loops around here and it traps the gas in there. Now if I add more mercury to the top and fill this thing up all the way with mercury, it's going to create a lot more weight down, and it's going to ultimately squeeze that gas into a smaller container, or smaller volume. So increasing the pressure here had the effect of decreasing the volume of the gas. You can see that, again here, kinetic molecular theory sort of explains the pressure change. If the volume of a gas is decreased, so going from 1 liter to 0.5 liters, the same number of gas particles is crowded into a smaller volume, and so there's more collisions with the wall. And so we can see here the pressure would go up from 1 to 2. And of course in a graph as well, if we graph the J tube, you can see here that the overall volume does decrease as the pressure exerted by mercury increases. Let's talk about pressure from the water. This is an increased pressure, right? You already have the weight of the ocean of air on top of you. Now you go underwater and there's water weight as well. So scuba divers learn about Boyle's law because it explains why ascending too quickly toward the surface is dangerous. The pressure regulator used in scuba diving delivers air at a pressure that matches the external pressure at depth. Otherwise, the diver would not be able to inhale the air. So if they are at, let's say, a depth of 20, there's 3 atmospheres of pressure on their outsides. If this scuba tank isn't forcing air into their lungs at 3 atmospheres of pressure, they won't ever be able to get it into their lungs because the outside pressure would be too great. When the diver's at that depth of 20 meters, there's already 1 atmosphere due to the air of pressure, and then 2 additional atmospheres of air of pressure due to the weight of the water. Every 10 meters will be another additional atmosphere of air, of what's the word, pressure, sorry. So, and then there's dangers of decompression. So a diver at 20 meters experiences an external pressure of 3 atmospheres and breathes air pressurized at 3 atmospheres. But if that diver shoots towards the surface with a lung full of 3 atmosphere air, his lungs will expand as the pressure drops to 1 atmosphere. So by being down at 20 meters with 3 atmospheres and then climbing up to 0 meters where the pressure is 1 atmosphere, look at how the pressure within the lungs will change. The pressure within the lungs, or the volume of the lungs, will go up. Pressure's going down, pressure's going from 3 to 1. So the volume, whatever the volume of your lungs are going to quickly get bigger. So this is why if you have a mouthful of, or a lungs full of air if you're underwater, then you need to breathe out while you're climbing up. And so divers must ascend slowly, breathe continuously to allow the regulator to bring the air pressure in their lungs back to 1 atmosphere by the time they reach the surface. Now this is if you go, if you're spending any amount of time down there at these below 10 meter diving. Now, of course, we'll talk about why you have to scuba dive if you're going to go below 10 meters, because snorkeling would not work for the same reason that you couldn't use a straw over 10 meters. Okay, let's do a Boyle's law example before we move on to Charles's law, and then we'll come back to the rest of the gas laws. So for this Boyle's law equation or a question, let's say we have a cylinder equipped with a movable piston. So we've got a container. That's the lid, doesn't match the cylinder. Okay. And it's got a movable piston. So let's say it's got this, thing's already kind of down in there. Okay, something like this. And let's say that we've got a volume in here of 6 liters, and already there's 4 atmospheres pushing down on it. Now, what's going to happen to this container when we change the external atmospheric pressure to 1 atmospheres? What's the new volume? So you should be thinking about how they're related, volume and pressure. When one goes up, what does the other do? And get an idea of what you think the answer should be. Should it be bigger or smaller than 6? I'll give you a formula. I guess sometimes it's shown the other way. P1V1 equals P2V2, but either one works here. So we need to identify what we have, and it doesn't matter if you call this scenario 1 and this scenario 2, or this one 1 and this one 2. You just need to pick. So we'll just go with this scenario 1, this scenario 2. We can plug in everything we know. We know the initial volume is 6. We know the initial pressure is 4. On the other side, we know the pressure is 1, but we don't know what the volume is. And then we rearrange. Now, I like to start with a rearranged equation. We're going for V2, so I like to say V1 P1 over P2 is V2. I like to get that actually before I start anything. That way when I go through and I plug stuff in, it's already all plugged in into the get-go, ready to go equation. If the pressure's going down, the volume should go up, and we should see that space within the cylinder expand. If you solve that, we're going to get 6 times 4, 24 divided by 1, so 24 liters would be the new volume of the gas. So as the pressure changes, goes down, the volume goes up. And we just need to check, does that make sense? And that it has the right units. The units here should be liters. All right. So, yeah, this little guy here, he's got an extra long snorkel. Now, why wouldn't this extra long snorkel work? So the diver at 10 meters is actually experiencing a pressure of 2 atmospheres that compresses the air in his lungs to a pressure of 2 atmospheres. And so if the diver had a snorkel that actually went to the surface where the air pressure was 1 atmosphere, and let's say they're at 10 meters down where the pressure is 2 atmospheres, air is actually going to flow that direction and not the other way around. It would be impossible to breathe, right? We don't suck air into our lungs. If he could somehow suck the air down, that would be one thing. But all we do is flex a muscle that expands our volume, which decreases our pressure. We're essentially, let's see. This is our lungs right here. We have a muscle that does this, that expands our diaphragm, expands our chest cavity. And because of that, air rushes into our lungs. And then we just let the air out. Okay. Let's talk about Charles's law. So why does hot air rise? Hot air rises because the volume of a gas at a constant pressure, at a constant temperature, volume of a gas at constant pressure will actually increase with increasing temperature. Let me think about what I just said there. The volume of a gas sample at constant pressure increases with increasing temperature. So this one is relating the volume and the temperature of gas, and we're going to keep the pressure constant. Presumably we would keep the number of moles constant as well. So in the last one we were looking at temperature and moles as constants. Here, pressure is a constant. So in order for now, of course, if volume can affect, if temperature can affect volume and pressure can affect volume, then we would never know where the effects are coming from. So we have to isolate them. So that's what we're doing here. So we're going to say that pressure will remain constant. Now, as long as the amount of gas also remains constant, then warming a gas will actually decrease its density, because if you remember, density is your, I was going to put grams, it's your mass over your volume. So raising the temperature increases the volume of the gas. And we're going to talk about how that happens. So as you heat the air in the balloon, it makes the balloon expand. Now why? This is because the gas molecules get energy, which means they start bouncing around inside the balloon faster. Okay. We said, though, that pressure was going to stay constant, right? This, of course, would increase the pressure within this balloon, correct? If the gas molecules are moving around faster. So the only compensation to keep the pressure the same is that the volume of the balloon has to increase. That offsets the effect of their increased speed, because now they have to go farther, right? We saw that as the volume gets bigger, pressure goes down. So when pressure stays the same, that just means that the volume is going to be a function of the temperature. So temperature is going to be proportional to volume. And so in a hot air balloon, right, the air around the hot air balloon has its own density. And the density of the air in the balloon, let's call it density balloon, when it's on the ground is the same. They have the same density. But as you start to apply heat to this air, and because the volume is going to expand, as long as the mass doesn't change, the volume gets bigger. So the mass over the volume, that ratio means a lower density. And that means the density of the balloon is now going to be less than the density of air, and so it's going to rise in air. We can accomplish this without heat by just using a lighter gas, like hydrogen or helium. Turns out hydrogen is flammable, helium is expensive. So that's why heating air is a low-cost solution to this. Now we can plot this relationship and see it very clearly that as we increase the temperature, the volume of a gas will go up. I have a video I will try to find and post for you. It's of me playing around with some liquid nitrogen in a balloon. I've got a little pan. Actually, I don't have a pan. I'm just doing it on the lab counter there at COS. I've got a balloon, and I'm pouring liquid nitrogen from what they call them dewars. And so the liquid nitrogen is really cold. Liquid nitrogen, as it's hitting the balloon, it starts to cool the gas within the balloon, and the balloon starts to shrivel up. Shrivels up almost completely flat because of all the coldness has reduced the motion of those particles so low that for the pressure to stay the same, the volume has to shrivel up. And then as I let it warm up, just in the lab classroom, it like inflates again. It's really cool. I'll see if I can find that. If I can't find it, and if you don't want to wait, then definitely just like YouTube that liquid nitrogen balloon. You could do something at home like this. You could kind of half fill up a balloon, or at the very least, just put a little bit of air in it and tie the balloon off, and then put it in some boiling water on the stove. Hopefully a pan big enough that it's not just going to pop when it touches the sides, but if you let it sit in the boiling water, as the water gets hotter, the balloon will start to inflate. It'll be kind of cool. Okay, so we can predict with that graph, we can actually predict the volume of a gas based on its temperature, and we can also kind of, using the volume, predict the temperature of the gas. It doesn't really work. It's not really that the volume is determining the temperature. It's kind of the temperature determines the volume. So it's more something that we try to use the temperature to try to figure out. Now this is the reason that we use Kelvin, because if we were to start using negative degrees Celsius, you start to see here that we can't divide by well, we can divide by negative numbers. That's not a problem. As we start to go down in Celsius from things like 36 degrees Celsius down to where, if we go back to this table real quick, you see that in Celsius, we can have really low temperatures, like negative 300. If we start to go negative, we have to pass through 0 degrees Celsius, right? And sometimes that means we're going to have to divide by 0, and we can't do that. So the better thing to do is, rather than use Celsius, which has a big stretch of negative numbers, is to use Kelvin. Kelvin goes down to 0, which is absolute 0. So really every temperature above absolute 0 is going to be a positive number. And so we're going to use positive numbers here when we deal with our temperature. We're going to use Kelvin. So in Kelvin. Now Kelvin doesn't get a little degrees symbol like Fahrenheit and Celsius do. Now Charles' law was actually formulated by J.A.C. Charles, a French mathematician and physicist. It relates the volume of a gas with the Kelvin temperature, and it is, again, proportional. So if two variables are directly proportional, then that means increasing one by some factor actually increases the other by the same factor. So if we double the temperature of a gas in Kelvin, then its volume doubles. When the temperature is tripled, the volume triples, and so on. The observed relationship between the temperature and the volume of a gas actually follows from kinetic molecular theory. This is why it's a good theory. If the temperature of the gas is increased, the gas particles move faster, and the pressure has to stay constant, so the volume must then increase. All right, so Charles's law can be used to calculate the volume based on a temperature, and we have this equation here. V1 over T1 equals V2 over T2, where the pressure and the amount of gas are constant, so they're not included. And you can see here, it doesn't matter if you have which one's V1 or which one's V2, as long as you keep it paired properly with the correct T1 and T2. So let's do one of these problems. So let's say that we have a sample of gas that has a volume equal to 2.80 liters, and it's at an unknown temperature. We don't know. When the sample gets submerged in ice water at temperature 0 degrees Celsius, so let's just say some other temperature, when it gets submerged in ice water, the volume decreases to 2.57 liters. So the question here is, what was its initial temperature in both Kelvin and in degrees Celsius? Degrees goes over here. And assume constant pressure. So we are given the initial volume, the final volume, and the final temperature. And we're asked to find the initial temperature in both Kelvin and Celsius. So the first thing we need to do is we need to put our temperature into Kelvin so that we can use the V1 T1 V1 over T1 equals V2 over T2 equation. Now we're solving for T1 here. So let me just point this out, because students often make this mistake. This is why I had to do the math review at the beginning. So we want T1 by itself, so we cannot just divide by V1 and call it a day. T1 does not equal V2 over T2 times V1. So we have to, now, I mean, if you do this, you have to flip everything over. We can take the reciprocal of everything and just say this, and this is true. But what you want to do is you want to realize at first that your T1 is on the bottom of a fraction. You don't want it there. So you want to multiply everything by T1 to get it up top, and then move everything over to the other side. So that would have left us with the V1 over here, the T2, and then the V2 would have gone down here, And so again, if you get the T1 by itself on the bottom of a fraction, just flip everything upside down. So let's plug in everything we know. We know that V1 is 2.80 liters. We know that T2 is 0 degrees Celsius. Now we don't want Celsius. So plus 273 will give us Kelvin. And it just so happens that that's a nice, easy math for us right there. 0 plus 273 is still 273. Volume 2, we were given 2.57 liters. Now, just a thought part of this. If we lowered its temperature, or I'm sorry, if we put it into 0 degrees water and its volume went down, so it was 2.8, now it's 2.5, was the initial temperature hotter or colder than 0? That's what you should be thinking about. Okay, so we solve for this. This comes out to be 24 degrees Celsius. 24 degrees Celsius, sorry, that's not the right answer. This comes out to be 200 Kelvin is what we were going for. So when you solve this, you get 297 Kelvin. Now, we need both Kelvin and Celsius answers. So we just have to undo the adding 273, and that gets us back to the 24. So 24 degrees Celsius, 297 Kelvin was the initial temperature. You can solve, or be asked to solve, any one of these variables. T1, V1, T2, V2. But you'll be given all three of the other variables. All right, so we have a combined gas law. Now, the combined gas law brings temperature, volume, and pressure all together. So Boyle's law shows how P and V are related at constant temp. Charles' law shows how V and T are related at constant pressure. So what if these two variables change at the same time? And that's what we're kind of seeing here. So let's say we have a sample of gas that has a volume of 158 milliliters at a pressure of 735 mmHg. Temperature is 34 degrees Celsius. And then let's say the gas gets compressed to a volume of 108 milliliters. And actually heated to a temperature of 85. What is going to be the final pressure? So we can't just say, oh, the temperature, the temperature went up, so the pressure's higher. Well, the volume went down, so that would make the pressure higher too. It looks like both of these actually are going to make the pressure higher. So we can use some logic here. P2 should be higher than P1. So we can do that, but that doesn't tell us how much higher. So let's draw a strategy plan. Let's try to figure this out. So we know we need P2 by itself. So I'm going to rearrange my formula right off the bat and just get the formula for what I do need. P2. P2 is going to be equal to P1 V1 T2 over T1 V2. Just getting P2 by itself. We need to know what T1 and T2 are in Kelvin. So plus 273 for T1. And plus 273 for T2. All right, so we can plug everything into our equation. 735, I'm lazy, so I'm not going to put all the units in there, but you definitely want to keep putting your units. In this event here, we have milliliters, but because we're going to divide by milliliters, the unit cancels, and so we don't have to put it into liters. That was the temperature, and then 108 milliliters. So if we had put the units, our kelvins would cancel, our milliliters would cancel. So you just want to make sure you're in the right units. And then this is mmHg here, pressure. We would get 1.25 times 10 to the 3 millimeters of mercury, or 1,250. So P2 is higher than P1. So that's a bigger problem. That's about as big as they get now. You could have been asked for atmospheres instead of millimeters of mercury. That makes it a little harder. You could be given, Fahrenheit instead of Celsius. That would make it harder. All right. One more law. We've got Avogadro's law. Now, Avogadro's law is what happens when you change the amount of gas um, inside a container, or add more gas molecules. So you can see that if we add more moles, the volume has to increase. Now, this, of course, is going to make constant um, the pressure and temperature terms. So if pressure is going to stay constant and temperature is going to stay constant, then as we increase the amount of a gas, the volume has to get bigger to accommodate. This makes sense if you've ever blown, gas molecules. If you ever filled up a balloon, right? You blow air into a balloon. The balloon gets bigger. It has to. Okay. So the volume of a gas actually increases linearly with the number of moles in the sample. And this was first formally kind of stated by Amadeo Avogadro. This is called Avogadro's law. And again, volume is going to be here proportional to the number of moles. And this one's really intuitive. As you blow into a balloon, it makes sense that you're adding gas molecules and then increasing the volume. Let's do a problem with Avogadro's law, just a real quick one. Let's say that we have a 4.8 liter sample of helium gas. So let's say it's a balloon that's 4.8 liters, and it's of helium, and let's say that there's 0.22 moles of helium inside that balloon. Now, the question is, how many moles helium do I need to add in order to get a balloon that is 6.4 liters? Okay, and so the relationship that we would find here is similar to that of the proportionality between volume and temperature, in that V1 over N1 will give us V2 over N2. Okay, we want to know how many moles of helium. We know V1 is 4.8. We know N1 is 0.22. We don't know what N2 is. So we need to solve for that. So we would solve for N2. N2 is going to be on the bottom of that fraction. So again, we need to rearrange it. N2 will equal V2 over V1 N1. We can plug in our values here. 6.4 liters over 4.8 liters. 0.22 moles. Liters will cancel, and we get 0.29 moles. Now the question is this the answer? Is this how many moles we have to add? And the answer is no. We already have 0.22 moles in there. We just need to get up to 0.29. And so the answer is 0.07 moles. So it's not a trick question, it's a critical thinking question. The question what we were solving for was, how many moles of gas do we need to add to get to 6.4? And the trick here is knowing how to use this equation to both find out how many moles of gas there would be at 6.4, but then also to know that we just need to subtract what we already have to get to that total. Hopefully this problem wasn't a confusing one for you. Again, all of these that we're looking at are focusing on just one aspect, moles or pressure or volume. We are going to mix them all together. All right, so the ideal gas law can actually combine Boyle's law, Charles' law, and Avogadro's law all together into a single law. So we know that volume is proportional to the inverse of pressure. We know that volume is proportional to temperature. We know that volume is proportional to moles. So as such, volume is proportional to NT over P. We have a R constant, which is a proportionality constant that we can insert, and we get the R equals R NT P, or often PV and RT. So we see a little bit of rearranging in order to get it into the form that people typically see. Now, let's talk about this R constant. This R constant is what happens when we substitute values. Well, first we could solve for R. R is equal to the volume times the pressure over the moles times the temperature. And we can see if we were to plug in 1 mole and use standard temperature and pressure, standard temperature being 0 Celsius or 273 Kelvin, standard pressure being 1 atmosphere, and volume of 1 mole of gas at the standard temperature and pressure is 22.4 liters. If you plug all these numbers in, we get that R in the units of liters, atmospheres, moles, Kelvin is 0.0821. Now I've included that term on your formula sheet that I gave you for your exam. You should use that formula sheet for each of your exams. It does have all the good formulas on it and the good constant values. So if we were to plug in a different value, let's say of 760 millimeters of mercury here, instead of the 1 atmosphere, we actually get a different R value equal to 62.4 liters torr or millimeters mercury moles Kelvin. Torr and mmHg are the same. So you will see a different R constant. But if it has pressure, volume, mole, and temperature units, then it is usable in these equations. Just be aware that if you use this R, it's assumed that you're dealing with a pressure and torr. But you can find an R constant for pounds per square inch if you're interested in that. So here are the forms of the equation that you can use when you have certain variables. So if you're looking for V and P, then you might as well just use the Boyle's law, the simplified version of the ideal gas law. But you can see here that the ideal gas law basically contains all of the gas laws in it. All right. So let's use the ideal gas law in calculation. So let's not do a molar mass one yet. I don't think we're there. Let's do just a general gas law equation. So let's say that we have some moles equal to 0.845. We have a pressure for our gas equal to 1.37 atmospheres. Let's say the temperature of our gas is 315 Kelvin, and I want to know what the volume is. Okay, so we're given all of this. We've got our equation PV equals nRT. We need to solve it for V. V equals nRT over P. We just need to plug in the values now. N, of course, is 0.845. For the R constant, 0.0821. Pressure, we're going to say is, pressure's on the bottom. Temperature is 315, 1.37. Sorry, my sloppy penmanship got out of control right now. If you solve for V, and you should take a minute, pause the video, solve for V, you should get 16 liters. Now this was just a question where we weren't looking at any changes. We were just using the information of the amount of the gas, the pressure of the gas, the temperature of the gas to predict the volume of the gas. All right, now the value of this answer is a little more difficult to judge than, kind of just intuitively feeling if that makes sense or not. It's worth noting that if you have a volume of a gas if you have 1 mole of a gas at 1 atmosphere, so let's talk about that real quick. Standard temperature and pressure, this being 1 atm, this being 273 Kelvin, then the volume of 1 mole should be about 22.4 liters. Now that being said, we have a slightly higher pressure, so the volume should be slightly lower than 22.4. And additionally, we don't have a complete mole of the gas. So the fact that we have 16 as an answer seems reasonable. We could solve the molar mass of a gas from the ideal gas law. And I wanted to take a minute and do that. That's typically a problem that you can do in the Chem 20 level. So what we'll do is we'll use the ideal gas law in combination with a mass measurement. Because molar mass, if you remember, is your grams per mole. So if we know the moles and the grams, we can solve this. Even if we know the ratio of how much some number of moles weighs, we can figure out what 1 whole mole would weigh. So let's say that a sample of a gas has a mass of 0.136 grams. So that's how much our gas weighs. Now we don't know how many moles we have, but as far as molar mass goes, we're halfway there. We already know the weight of our gas, we just need to know the moles of our gas. Now this gas has a volume of 0.112 liters at a temperature of 298 Kelvin and at a pressure of 1.06 atmospheres. Liter, atmosphere, mole, Kelvin. What would N be? So we can use PV equals nRT to solve this. N is going to equal PV over RT. We plug in all of these numbers and solve for N. So go ahead and give that a shot. Pause the video. I'm going to give you the answer. 4.525 4.525, 4.8, 525. Times 10 to the minus 3 moles. There's a number of sig figs we can keep. I think it's 3, 4.85. We would then take that number of moles, stick it into this equation, the molar mass. About 28 grams per mole. If we knew how many atoms were in this gas molecule or what kind of gas molecule it is, we could kind of figure out what it was. If we had some clues, I think it might be, tell me if you think you're right. I'm right with that. Okay, so that is solving the molar mass of a gas from the ideal gas law. So we used the ideal gas law in conjunction with just some information on mass in order to do this. Okay, so gases are not always acting ideally. So we've been talking about ideal gases. Let's talk about situations when they don't act ideally. So at low temperatures and high pressures, we tend to see non-ideal gas conditions. So let's look at the ideal conditions first. So at high temp and low pressure, particle size is small compared to the space between particles. You can imagine at, so ideal gas conditions work best at high temperature and low pressures. The interactions between the particles are insignificant. In the non-ideal gas conditions, so what we're talking about here is ideal gases, and when our gas laws can actually match up with the ideal gas conditions. So our ideal gases, or real gases, match up with our gas laws at high temp and low pressure. But where they don't match up is at low temp and high pressure. Now the reasons for that: at low temperature, there's not a lot of particles bouncing around, not a lot of energy, also not a lot of volume, as we can kind of see. And that's the same case at high pressure. The volume is really small. So when the volume is really small, we get two problems. We get volumes that don't match up because the particle size of these gases is a big, a big influence on the volume of the container compared to the spaces in between them. Whereas in the ideal gases, we don't have to worry about the size of the molecules. We could just talk about the size of the space that they're interacting in. So the volumes that we tend to see when we use the ideal gases, or the ideal gas law on real gases, we tend to see bigger volumes than are predicted, and those bigger volumes come from the fact that these guys actually have mass volumes of their own that matter. The other thing we see is that there are interactions, and these interactions sometimes lead to lower volumes than we would predict. Temperatures and volumes are related, but we would see smaller volumes, and the reason for that is when the gases get too close to each other, they start to clump together, and that reduces the volume at low temp to what is even lower than what we would have predicted. So this is just showing you how ideal gases differ from the real thing. Real gases are non-ideal, and sometimes we can still work with them in the best conditions, but in some conditions we start to see deviations from the laws. All right, let's wrap up our lecture with partial pressures by talking about partial pressures. So according to kinetic molecular theory, each of the components in a gas mixture actually acts independently of the others. So the pressure due to any individual component in the gas mixture is actually called the partial pressure of that component. So the partial pressure of any component is that component's fractional composition times the total pressure in the mixture. So that might be a little confusing. Let's use an example. In our air, in our atmosphere, the mixture is about 78% nitrogen, about 21% oxygen, about 0.9% argon, 0.04% carbon dioxide, and there's a few other gases in smaller numbers. Now, because the nitrogen gas because the nitrogen molecules in the air exert a certain pressure, 78% of the total pressure, that is independent of the presence of the other gases. And same thing with oxygen. The oxygen molecules in the air exert a certain pressure. It just happens to be 21% of the total pressure. And since partial pressures are just the fractional composition times, fractional composition is the percent composition divided by 100, but then the percent is just times 100. So we'd kind of be doing some circular stuff there, but I'll show you what I mean. So the fractional composition of nitrogen would be 0.78 because it's the percent times divided by 100. That's how you get to the fractional composition. So 0.78, or the decimal percent, right? And for oxygen, it's 0.21. Again, for this guy, it's 0.09, and this one would be 0.004. Then we multiply it by 100. So, or my bad, we multiply it by the total pressure. Now, in our case, if we use atmospheres, that's the easiest because atmospheres is, just one. So 1 atmosphere times 0.78 is going to give us 0.78 atmospheres. So the partial pressure due to nitrogen is 0.78. The total pressure is still 1, right, at sea level, but 0.78 of all of that comes from the nitrogen. And we found that out because it's just the fractional composition of the nitrogen in the air in the mixture times the partial pressure. So for oxygen, 0.21 times 1 leads to a 0.21 atmospheres. So the partial pressure of oxygen, which we would designate as PO2, is going to be 0.21. Let's use the example in this picture here just to kind of round things out with two examples. This mixture has two gases in it, helium and neon. Helium is 0.8 decimal percent of the whole mixture, and helium is 0.2. if we multiply this by 1 atmosphere, or the total pressure, we get the partial pressure. And there's a formula. It looks like this. Partial, or I guess we could call this, I guess we have a symbol. So, for example, if this was partial pressure of O2, this would be the fraction of O2. This is a chi symbol. This means mole fraction. This actually represents the moles of O over the total moles. But that's the same thing as saying percentage, right? Part over the whole is percentage. And that is what we've got here in these decimal percentages when they've already told us the percent composition. In Chem 1, you're not given those. You're not given the 80 and the 20. And you have to find it out yourself with the mole fraction. And usually they don't tell you the moles. They tell you how many grams of each gas you have. So you can imagine that that just gets to be some calculating. But in the end here, the mole fraction, or the fractional composition, the decimal percent, that gets multiplied by the total pressure. And that will give you your partial pressure. So in the case of the helium here, it's 0.8. In the case of the neon, it's 0.2. And if we were using torr, this would be 760 torr, then these answers would just be in torr. 0.8 of 760 is going to be like 720 or something like that. I don't know if that's the right, it's not, but it's going to be a big number like that. It's going to, and it'll be in torr. So that's how we do these. Okay, so let's see, I think I have another formula to give you actually before we move on to that picture. So there's also a law of partial pressures that says that the P total is just a sum of all the individual partial pressures. So you might have gotten that from the fact that the partial pressure of helium and the partial pressure of neon add up to be the total pressure. But this is formally kind of showing you that. So same thing for air. The partial pressure of nitrogen gas, oxygen gas, and argon, which made up the majority, was 0.78, 0.21, and 0.01. If you add these all up, you basically get 1 atmosphere. So partial pressures add up to get total pressure. Let's do a typical problem. This one's really easy. And these partial pressure problems are typically easy. Let's say we have a mixture of helium, neon, and argon. And the total pressure, let's call it P-tot. Total pressure is 558 mmHg. And I'm going to give you the partial pressure of helium. Partial pressure of helium is 341 mmHg. Partial pressure of neon is 112 mmHg. And the question for you is, what is the partial pressure of argon? Argon. All right, go ahead, pause it, figure it out. I'm going to tell you the answer. It's kind of like the conservation of mass type problem. Here, the partial pressures have to add up to the total. If you're given the total, and even, well, you'd have to be given most of the partial pressures, all but one, you can find the answer. Our lungs have actually evolved to breathe oxygen at a partial pressure of 0.21 atmospheres. And so you can see that at the surface. I'm going to give you an example when we go in an airplane, or if we go into an increased elevation, or in this case, if you're scuba diving. But if the total amount of if the total pressure decreases, as what happens when you climb a mountain, or if you go up, any kind of decreased oxygen environment, the partial pressure of oxygen also decreases. So on the top of Mount Everest, for example, total pressure is only 0.311 atmospheres. So the partial pressure of oxygen is only 0.065. And when you're in a low oxygen condition, that's called hypoxia, or oxygen starvation. It could cause dizziness, headaches, shortness of breath. Severe hypoxia actually occurs when it drops below 0.1 atmospheres, and that can actually cause unconsciousness or even death. So climbers hoping to make it to the summit of Mount Everest usually carry oxygen for them to breathe. High oxygen levels actually have negative physiological effects also. At 30 meters, we were talking about scuba divers having to breathe pressurized air. And if they're breathing regular air, this pressurized air has a total of about 40 atmospheres, right? If you were 30 meters, so it's an additional 10 meters from the previous examples we were looking at. This makes the partial pressure of O2 about 0.84 ATMs. And this increased partial pressure of oxygen actually causes a higher density of oxygen molecules in your lungs. And this results in a higher concentration of oxygen in your blood tissues. When PO2 actually increases beyond 1.4 atmospheres, the increased oxygen concentration in the body tissues causes this oxygen toxicity condition. And it's characterized by muscle twitching, tunnel vision, convulsions, and divers that venture too deep without oxygen or without proper precautions have drowned because of this toxicity. So normally scuba divers will breathe various mixtures of helium and other inert gases, helium and oxygen, because the nitrogen itself can cause a problem. At 30 meters underwater, partial pressure of nitrogen is 3.1, and this actually causes an increase in nitrogen throughout your body tissues and fluids, and this can lead to something called nitrogen narcosis at about 4 atmospheres. It's called the rapture of the deep. It's kind of like being tipsy. Judgment may be impaired, and if you want to avoid this, especially with people that like to scuba dive really deep, like beyond 50 meters, you have to use something that doesn't have nitrogen in it. So you would go with heliox or triox. These are different combinations of gases and oxygen that don't have the nitrogen, so you don't have to worry about the nitrogen narcosis. Let's see, do I have another partial pressure problem for us? I do. Do I have an equation? No. All right, let's do... I have a problem. Okay, calculate the pressure of oxygen that a diver breathes with a heliox mixture that contains 2% oxygen at a depth of 90 meters where the total pressure is 10 atmospheres. So we're calculating the partial pressure. We know what the decimal fraction is. We know what the total pressure is. Okay. So P total times decimal fraction equals partial pressure. In this case, we're looking at PO2. We're told the total pressure in this problem is 10 atmospheres. We're 90 meters below the surface, so 10 ATM. We're also told that the mixture contains a 2% oxygen, so 2%. We had to get the decimal fraction for that, so we divide it by 100 is going to be 0.02. Now this is a mole fraction, so it's unitless, and so we're going to get an answer in ATMs here. So this would be the partial pressure of oxygen that we'd be breathing with a 2% mixture at 10 atmospheres. So you can calculate how much, what your partial pressure would be. So we could fine tune a mixture with the right amount of oxygen so that we are getting normal oxygen levels. That's the benefit of being able to do a calculation like that. Let's talk about vapor pressure. When gas from a chemical reaction is collected through water, molecules or water molecules become mixed in with gas molecules. And so whenever we're capturing gases, this is one of the best setups because we can see the bubbles coming through the water, and we also know that they're all trapped, because they didn't leak out this way. What we're saying here, though, is that the water molecules themselves vaporize. There are some water molecules that are as gas form, and this is true at lots of temperatures. You can see even in your freezer, water does this. Water will leave your frozen goods and then turn into a gas, and then it condenses and refreezes on the inside of the lid or the bag. This is what freezer burn is. So the only way to do that, to avoid that, is to vacuum seal so that there's no air in there for, or no space for the water to evaporate into, no gas form. Anyways, the pressure of the water vapor in the final mixture is what we would call the vapor pressure of water. And so you can imagine that if we had this gas, we collected it, it's going to have a P total, and that P total is going to be the vapor pressure of the water plus the vapor pressure of whatever other gas. In this case, the vapor pressure of hydrogen gas, these little white molecules. So HCl dissolving some metal, zinc is going to react with two HCl's to form zinc chloride and a hydrogen gas molecule. And that's where that gas is being generated. So in one of the labs that we do, you guys are asked to quantify how much gas was formed from a reaction. And we do that by basically collecting the volume of the gas, right? The volume of the gas is how much gas we collect in this container. The temperature of the gas, we can measure the temperature with a thermometer. The pressure, we can use atmospheric pressure. But what you ultimately solve for is the moles of gas. But that's where the pressure comes in. What pressure do you use? Do you use the total pressure? Because that'll give you the total moles. You want to use the partial pressure of your gas that you're interested in. So you only get the answer for the moles of that gas. So you can see here that we have to subtract the vapor pressure of water often from chemical reactions or problems where we do like this, where we collect gas over water. So tables like this will show us what that vapor pressure is at different temperatures. All right. Let's see. I think I have an example actually here. So let's say hydrogen gas was collected over water at a total pressure of 758 millimeters of mercury and a temperature of 25 degrees Celsius. What's the partial pressure of the hydrogen gas? So remember, this is pH2 plus pH2O. At 25 degrees Celsius, the partial pressure of the water is 23.8 millimeters of mercury. So quick calculation, 734 millimeters of mercury. So you just subtract out the water. Now, in chemical reactions involving gases, gaseous reactants or products, the amount of the gas is often specified in terms of the volume, the temperature, and the pressure. So whenever we're going to use gases in a chemical reaction, they don't tell us, oh, you've got 3 grams of the gas. They just tell us the volume, the temperature, and the pressure. And the reason for that is because we can use the ideal gas law to actually convert from those pressure, volume, and temperatures into moles. And then we use the stoichiometric coefficients to convert from moles to moles in a typical problem. So I think we can do one. So let's do how many moles of NH3 are formed by the complete reaction of hydrogen gas with ammonia. So let's take some ammonia, some hydrogen gas. Let's say that we have plenty of ammonia. Make it easy. We're going to make plenty of nitrogen gas. I'm sorry. We're going to look for how much ammonia we can make. We need to balance this. Okay, so we have 2.5 liters of hydrogen gas. The temperature is 381 Kelvin. The pressure is 1.32 atmospheres. And the question is, how many moles of ammonia are formed from the complete reaction of all of this hydrogen gas with plenty of nitrogen? So we need to solve for N. So N equals, what did we say? PV over RT. So it's 1.32 times 2.5 over 0.0821 times 381. So moles of hydrogen gas ends up being 0.0155 moles. Keeping track of where our sig figs are. And then we have our stoichiometry that says in our balanced equation, 3 moles of hydrogen gas will react with 2 or will react to make 2 moles of NH3. 3 makes 2. So that would actually give us 0.07 moles of ammonia. So we can now take gas information, use it with our ideal gas law to find mole information of that gas, and then back to chapter 8, remember? Using stoichiometry. I mentioned this a little earlier, the volume of a gas, 1 mole of a gas at standard temperature and pressure, which is 0 Celsius and 1 atmosphere, is 24 liters, 22.4 liters, sorry. And this is true of any gas. So the conditions, standard temperature and pressure, are just used often in chemical reactions and just designated as STP. It makes doing experiments easy because then everybody can use the same numbers, and we can all use 1 in our calculation, right? 1 atmosphere. It's really easy. So the volume occupied by 1 mole of a gas under these conditions is called the molar volume. And the molar volume of an ideal gas at STP is 22.4. This is true whether it's helium. This is true whether it's xenon, whether or not you have different masses. Now we can actually take shortcuts then when we are doing calculations involving these kind of gases. Sorry, I'm trying to back up here to a blank page. Actually, I guess that's what I have my whiteboard for. Okay, so let's calculate the number of liters of a gas that forms at STP in this reaction. So calcium carbonate, solid, if we allow that to decompose, we get calcium oxide, solid, and carbon dioxide gas. So if we have 0.879 moles of calcium carbonate and it undergoes this reaction, how many liters of CO2 would we get? Now, we would typically have to figure out how many moles of CO2 we would get. Now, this is at STP. So we could, do a, we can find out how many moles. In this case, it's easy, right? 1 mole gives 1 mole. There's ones and ones here. So we would know N, we would know T, we would know P, we know R. We could use these to find V, right? Using the ideal gas law. But we could also, use that new conversion that we know of, that 1 mole is 22.4 liters. And we would do it like this. 0.879 moles of calcium carbonate. We know 1 mole of calcium carbonate makes 1 mole of CO2. And 1 mole of CO2 or 1 mole of any gas at STP is 22.4 liters. So without doing anything involving temperature and pressure, we can straightforward get our answer in liters from moles. So again, 22.4 liters is 1 mole. 1 mole is 22.4 liters. And this only works when we are at STP. All right, now air pollution comes from a number of sources, including electricity generation, motor vehicles, industrial waste. Some of the major gaseous air pollutants are the following: sulfur dioxide, produced in, primarily emitted during electricity generation and industrial metal refining. This is a lung and eye irritant. It affects the respiratory system. It's one of the main precursors of acid rain. There's carbon monoxide, formed by the incomplete combustion of fossil fuels, petroleum, natural gas, coal, and it's emitted mainly by motor vehicles. It displaces oxygen in the blood, causes heart and lungs to work harder, At high levels, carbon monoxide can actually cause sensory impairment, decreased ability to think, unconsciousness, death. We have ozone. Ozone is an upper atmosphere. It's a normal part of our environment. Um, Upper atmospheric ozone filters out part of the harmful UV radiation coming from the sun. And lower atmospheric or ground level ozone is a pollutant that results from the action of sunlight on motor vehicle emissions. Ground level ozone is an eye and lung irritant. Prolonged exposure to ozone has been shown to permanently damage the lungs. Nitrogen dioxide, emitted by motor vehicles, by electricity generation plants, the orange-brown gas that causes the haze, the dark haze often seen over polluted cities. NO2 is a eye and lung irritant, a precursor of acid rain, and again, all of these are bad for us. Now, at the beginning of the 1970s, Congress passed the Clean Air Act, requiring cities to reduce and maintain their pollution levels below levels set by the EPA, and these levels have decreased significantly over the last 30 years as pollutant levels have decreased over the last 30 years, even as the number of vehicles has increased. But according to the EPA, the levels of all four of these mentioned pollutants are decreasing during the 1980s to the 2008 area, or 2008 is when they announced it. 2014, I don't know about how they feel about those levels, those numbers. Air pollution plagues most cities, though, most large cities. And although levels of pollutants, especially ozone, in many cities are above what EPA considers safe, much progress, though, has been made. And this trend demonstrates that good legislation can actually clean up our environment. Numbers are getting better as we get more electric vehicles that don't produce these kind of wastes, which is ultimately the future. All right, in review, we looked at kinetic molecular theory, we looked at pressure, gas laws, the combined gas laws, the ideal gas laws, and we looked at partial pressure and vapor pressure of water. So hopefully these learning objectives help you narrow down your studying, and yeah, good luck everybody. Do the practice problems, hit me up on the discussion board if you have any questions, and keep at it. See you guys next time.